This is a demonstration of Agilent Technologies' optical extensions for instrumentation. There are two versions: the OXI modules, designed for and used with the PXI family of products, and the optical port extenders, designed for use with the PNA family of vector network analyzers. Let's take a look at the optical extenders in action. For our test setup, we'll use a vector signal generator to create and transmit our signal. And let's make two measurements. The first on an 18 GHz CW signal with the output power set to -20 dBm. And second, let's set up a QPSK signal modulated at 1 megasymbol per second to measure the modulation quality of a wideband digital signal. We'll receive the signal using a signal analyzer and make our measurements using the 89601B vector signal analyzer. Let's start with a reference measurement with low loss and compare it with other cables of various qualities and lengths. Then we'll replace the coaxial cables with the OXI links using 1 kilometer of fiber and compare the difference in signal strength and quality. For our reference signal, we'll use this 18-inch semi-rigid coaxial cable. This will provide us a low-loss signal path and a good comparison for all of our other substitute cables as well as our optical link. Let's take a quick look at our reference signal. I've placed a marker on the peak of the carrier, and a quick look at our marker readouts confirm that we're transmitting at 18 GHz at a power level of approximately -20.7 dBm, about 7/10 of a dB loss through our reference cable. Now let's turn on the wideband modulated QPSK signal, and we'll take a look at the modulation characteristics of this signal. As you can see from the band power measurement reading, we're still transmitting at about -20.7 dBm, and a quick look at the constellation display confirms that we have relatively little noise impacting our valid symbol states, and that's also reflected and confirmed in our EVM measurement at a 0.5% error vector magnitude. We'll use this table to log our test results. Once filled in, it will give us a quick comparison of the quality of each of our different transmission paths. For our 18-inch semi-rigid reference cable, we measured -20.7 dBm in both our CW mode as well as our modulated power mode. When we demodulated our QPSK signal, we came up with an error vector magnitude reading of 0.5%. Our path loss was 7/10 of a dB, which would result in a 50 dB loss over a 100-foot length. Next, we'll measure a 20-foot high-quality cable designed specifically for low power loss. These type of cables are high-performance cables that are designed for high-frequency, low-loss applications. Looking at the signal transmitted through our 20-foot low-loss cable, we can quickly see we've lost about 3 dB. We're now measuring -24.2 dBm. So let's turn on the digital modulation, recall our setup, and look at the modulation quality using our vector signal analyzer. From the band power markers, we can see the power level is the same at -24.3. The noise performance, as we can see from the symbol crossings in the constellation display, is still real good, and this is reflected in our EVM measurements at 0.5%. Let's return to our table and log the test results for our 20-foot low-loss coaxial cable. For CW power, we measured -24.2 dBm, and our modulated power came in at -24.3. Our EVM remained unchanged at 0.5%, and our path loss was 3 dB over the 20-foot length, which equates to 20 dB of loss over a 100-foot path. Now let's take a look at a piece of 50-foot RG142 and see how well it behaves with our signals. When we take a look at our measurement results through our 50-foot piece of coaxial cable, we can see our marker still at 18 GHz, but we're unable to make a good power level reading. We've got someplace between -90 and -100 dBm. Our only resort is to narrow this bandwidth to reduce the noise and see if we can make a measurement on our CW signal. As we get down approaching 200 kHz, we can see our signal comes up, and at 200 kHz, we can make a measurement of about -95 to -96 dBm. But at this narrow bandwidth, we're simply unable to transmit a wideband modulated signal. There's too much power loss in this cable for us to make a good measurement. For our 50-foot piece of RG142, we were able to measure minus 95 dBm, but only after we were forced to reduce our span down to 200 kilohertz in order to separate our signal from the noise. For a 1 megahertz wide modulated carrier, there's simply too much noise to be able to recover our signal, which prevented us from making a power reading or an EVM reading. Our path loss, 74 dB, or 150 dB for a 100-foot length. Now that we have a better idea of how our signal behaves through various lengths and qualities of coaxial cables, let's see how the optical links will treat our CW and modulated signals. Before we set up and make our measurements, let's take a look at how the optical links work. The optical links provides a wideband transmission path from 300 kilohertz to 26.5 or 50 gigahertz. The M9403A is a transmit module, modulating the RF signal onto an optical signal and transmitting it down a single mode fiber path. In our case, we'll be transmitting it down a 1 kilometer fiber path. The M9404A is the receive module, receiving the modulated optical signal and converting it back into an electrical RF signal. The M9405A is our 30 dB amplifier, used to overcome the conversion loss of the link. For our test fiber, we'll use the 1 kilometer cable found in this optical test box. So now let's take a look at our signal after transmitting it down 1 kilometer of fiber. We're measuring minus 33 dBm. Let's turn on our digital modulation and turn on our vector signal analyzer, and you can see real quickly by the constellation display and the valid symbol states that we've got a real low noise signal here, which is also represented in our EVM of 1%. So we've been able to transmit a signal down 1 kilometer of fiber with 1% EVM. Let's complete our table and compare the results. The optical links were able to deliver a signal level of minus 33 dBm for CW and modulated power. Our EVM came in at 1%, and our path loss about 12 dB a loss. On equivalent terms, this is 0.4 of a dB per 100 feet. So what did we learn? Well, as we know, noise is a constant battle. We can tolerate the signal loss in coax over short distances, and if we use a high-quality, low-loss cable, perhaps up to 100 feet. But in RG142, 50 feet is simply too much. The optical links, on the other hand, are able to easily complete a 1 kilometer transmission path, delivering an excellent signal-to-noise ratio well beyond the capabilities of coax. Now that we've seen how well the optical links perform, how can we justify the $65,000 investment? As we've seen, there are a wide variety of coaxial cables available for both low-loss and high-frequency requirements. The price of these cables vary widely with the quality, but attenuation always increases with the frequency and length. The performance of the coaxial cable degrades over time, and they are highly susceptible to damage. The return on investment, or ROI, will depend upon the amount being spent to maintain the coaxial signal path. As stated in our example, if the yearly replacement cost of the coaxial cables is $10,000, the price of the optical link could be justified over a 6.5-year period. The second justification is when the amount of attenuation over my signal path is simply unacceptable. If my signal path is 100 foot or greater, it is very difficult to overcome the attenuation in the signal path. Finally, we can justify the links based upon eliminating the hardware required for remote down conversion techniques. The remote mixer requires a remote local oscillator and IF amplifier. In this example, the additional hardware required exceeds the cost of a single optical link and is far more complex, forcing us to deal with the undesired mixing products of the down conversion process. That concludes Agilent's optical extensions for instrumentation. The optical link modules come in a PXI form factor and are modular, scalable, and upgradable. And the optical port extenders come in a form factor to complement the PNA vector network analyzers. For more information, please contact your local Agilent sales representative.